Welcome back to part 3 of chapter 5, Introduction to Modern Symmetric Key Cipher. Let's not waste time. Where are we here? Okay, so there are 6 components, yeah? There are 6 components and we have finished P-box. So let's look at the second component, S-box. S-box, S comes from substitution. So substitution box can be thought as a miniature substitution cipher. So just like P box, you have M times N, yeah, plain text size times ciphertext size. S box also, yeah, is that way. So you can draw the mapping of an S box like this, a table like this. So the following table defines the input-output relationship for S box. So the outer, the darker gray, the numbers in gray color box is the input. So M times N, yeah, plain text mapped to ciphertext. So this is the input. Right? And the inner, the white block is the output. So first, how do we read this? Okay, leftmost bit, LSB, right, leftmost, MSB, yeah, MSB, left. So to read this, 0, 0, 0, 0, 0, 0. So what is the white box? The input is 0, 0. Okay. How about this one? 0, 0, 1. So 0, 0, 1 is mapped to 0, 0, 1 is mapped to 1, 0. See? All right. So like the example says here, an input of 0, 1, 0 yields the output 0, 1. Yeah. An input of 1, 0, 1 yields the output of 0, 0. So that's how you read this. Okay, let me ask you a question. So is this invertible? Is S box invertible or non-invertible? What do you think? Okay, keep in mind, think about it. Let's go on to the next slide. Here. An S box may or may not be invertible. It depends on how, what kind of box you have for the S box. Here, this is 3 input times 2 output. So 3 by 2 S box. So this is non-invertible. Yeah, because, all right, you have because, okay, let's see. All right. In an invertible S box, okay, keep in mind, and in an invertible, if it can be inverted, the number of input bits should be the same as the number of output bits. Okay, look, 0, 0 becomes 0, 0, 1. So when you do the decryption table, here what, I give you an example, 0, 0, 0 becomes 0, 1, 1. So you can invert it the other way around. 0, 0, 1 becomes, 0, 1, 1, sorry here. 0, 1, 1 becomes 0, 0, 0 when you invert, right? But, yeah, a 3 by 2, you cannot do that because this is input, this is main text, this is ciphertext. Okay, so you got this. But when I try to do, the outer is ciphertext, so I only have 2 bits. If my outer is only 2 bits, so it is either 0, 1, 0, 1, right? So I have only 4 box. But in fact, I actually have 8 input box. Yeah. So I cannot fit in 8 into only 4. So that's why, yeah, if you have different size of input output in the X box, that is non-invertible. But if you have the same size, it's invertible. So that is S box, very easy. Yeah. So S box, remember, it's not permutation like pre-box just now where we have mapping arrow. Here is just, yeah, if the input is 0, 0, 0, you replace it, you substitute it with 0, 1, 1. If the input is 1, 1, 1, you replace it with another bit, 1, 1, 0. So substitution. Okay, done with the second component. The third component is very easy, exclusive OR, XOR. I'm sure you have used this, yeah, XOR. XOR we use a lot in cryptography, in computer science, yeah. So XOR table is like this. Okay. This is the input, yeah, this is the input, this is the output. If the bit is the same, 0 XOR 0, 1 XOR 0, then your output is 0, false. Yeah. But if your input is opposite, 0 XOR 1 or 1 XOR 0, then your answer is true, 1. All right. So what's interesting about XOR and why it is very useful in cryptography is because you can get the same result when you decrypt, when you do it the other way around. So look, so if this is input plain text, you XOR with the key. So X, input plain text, XOR with the key, you get ciphertext Y, you get Y. So when you decrypt your Y, you decrypt key with the key, do you get back X? So I replicate Y here, I put it here Y, I keep K as it is because we're using the same K, right? And then I use the XOR because it's the XOR component to get, do I get back X? So 0, 0, yeah, if they are the same, XOR says it is 0, 0. If they are opposite, XOR says it is 1. And I compare this. Do I get back my original text? Yes. So this proof that XOR is a great component where you can do encryption decryption easily because it fits the criteria. Yeah, you can invert. All right, the invertibility of the exclusive OR operation. It can be inverted. Okay, P box, X box, Xbox. No, Xbox is a game. P box, S box, X OR. Okay, 3 out of 6. What's the fourth one? The fourth one is our basic. I told you, you will look at me like, man, it's getting easier and easier. P box was, whoa, a lot. And the S box, okay. XOR easy. Now circular shift. Don't you know what circular shift is? Yeah, right. You shift, but when you get to the last one, every time you shift, if you get to the last one, you bring it back, yeah, to the beginning. So here, yeah, if you shift, before shifting, 7, 6, 5, 4, 3, 1. So if it says shift left 3 bits, yeah, so you just shift it 0 here, 3 bits. 1, 2, hold on, shift left. Yeah, that one is going left, isn't it? Okay, sorry. This is not left because this is going right. Erase. All right. So shift left is actually left. So 3 left. 1, 2, 3. So look, B0 is here. Yeah. Okay, how about number 4? 1, 2, 3. B4 is here. So just shift everything left, and then after shifting, you get this. If shift right, okay, right. 1, 2, 3. So 7 is here. B7, you bring B7 there. Yeah. So it is circular shift. Okay, what does circular means? You bring it back. So if I want shift right 3 bits, so okay, let me do a different color so you can see. So here B0, 1, 2, 3. You circle it back. That's what we call it. Circular shift. Okay. 4th is done. Easy. 5th, swap. Left to right, right to left. Ta-da! The swap operation is a special case of a circular shift where k is n divided by 2. Okay, never mind. It's just you swap left to right, right to left. You'll see that. Yeah, we'll use it a lot in either encryption or hash value hashing and so on. Okay, so if the blue one is left, after encryption, the blue label becomes the right part. Yeah, and then white becomes, so just swap. And the final component of a modern symmetric cipher is split and combine. As the name says, if you have 8 bits here, you split it in encryption. Split 4 here and 4 goes the other side. Again, you will see this. And when you decrypt, when you have 2 different sides, you combine it. That's what we call it, split and combine. Ta-da! So what are the 6 components of modern symmetric cipher? P box, S box, XOR, circular shift, swap, split, and combine. So after knowing all these 6 components, you can create your own symmetric cipher. I actually taught a student. Okay, maybe I'll explain this in the discussion. I'll tell you the story in our discussion. Okay, so that is modern block cipher. We are talking about block, where, remember, we start off at the beginning with how to input the padding bit. How many padding bits we need if our block size, we don't have full bits in the last block. So that is block cipher. Let's continue because we only have 12 minutes so far in this part. What is this? Part 3? Part 3. Yeah. Cipher, the modern kind, can also be stream. Block is where you have, you split it into different chunk of block. But in modern stream cipher, encryption and decryption are done R bits at a time, whether 1 by 1 or 2 bits by 2 bits or 3 bits by 3 bits. Yeah. So we have a plain text bit stream. Okay, and then we have a ciphertext bit stream, yeah, that was produced when we encrypt the plain text bit stream with the key bit stream. Okay, so in modern stream cipher, all right, we have synchronous or non-synchronous. All right. So modern block cipher, we only look at modern, we look at the component. Then we look at stream cipher. Stream cipher, there are 2 kinds, synchronous and non-synchronous. So this is a stream cipher. Stream, like water stream, river stream, yeah? Continuous. So continuous stream of plain text, encrypt with continuous stream of key. So P1 encrypt with K1, it will produce C1. P2 encrypt with K2, produce C2. So you don't have to split into different blocks. This is stream. Just go along, follow the stream. Okay? So in a synchronous stream cipher, the key is independent of the plain text or ciphertext. You will see later on in block cipher sometimes, or is it most of the time, you create the key from the plain text, or the final key, you have a key, but then after some permutation and substitution and with certain parts of the plain text to create key. So they have connection, they are related. But in synchronous stream cipher, they are independent. Your key doesn't it's created without any influence from your plain text or your ciphertext. All right, in synchronous stream cipher. I'm imagining I'm in a river. Okay, so the first component, oh no, the first technique, or maybe the only technique, a technique that I will show you in synchronous stream cipher is called feedback shift register, FSR. Yeah, or we actually, the one that I want to show is actually LFSR. Yeah, linear feedback shift register. So let's just go into this one, example 5.18. So it says here, create a linear feedback shift register with 5 cells in which B5 equals to B4. This is, if you're not familiar, this is a symbol for XOR. Yeah, this is a symbol for XOR. B4, XOR B2, XOR B0. Okay, maybe I can. All right. So what happened is, first, remember we have a stream of plain text, XOR with a stream of key, and then we get ciphertext. So here, this linear feedback shift register, actually, what we're doing here is creating the key first, which in this synchronous stream cipher, we don't have any connection. It doesn't depend. It is independent of plain text or ciphertext. We only have origin. Okay, this is your key. Okay, produce. This is a number, your shift register, produce. Okay, so if you want to imagine shift, maybe because you didn't take logic digital, but if you have your electrical background, you may know about logic digital. So in logic, we have shift register. Yeah, shift. Okay, what is shift register? You know you have memory, right? Memory, external memory, smaller memory, internal RAM memory. Then you have so the smallest memory in our computer is shift register. So your external can have 2 terabyte. Your internal can maybe also now have, like 512 SSD, your RAM. Yeah. But this shift register, they only keep 1 bit at a time, which actually is this. Yeah. If you learn computer organization and architecture, you will know this. Okay. So you imagine shift register as not imagine, it is the smallest memory in a computer. So in this case, it holds only 1 bit. So you imagine a box that can keep either 1 bit, bit 1 or bit 0. That's all. So we have 6. We have 6 boxes because we start with B0. So B0, B1, B2, B3, B4, B5. B5. Wait, B5. No, B5. So 6. Yeah, we have 6 shift registers, 6 boxes that holds either bit 1 or bit 0. So 6 boxes. 1, 2, 3, 4, 5. Wait, you said 6. How come there's only 5? Okay. Okay, hold on. The last box, the B5, is created from a manipulation of the other 5 boxes, 5 bits. All right, so it actually has a box, but we don't do the box there. So the B5 is just, we write it there. Yeah. Okay. So first, yeah, we have these boxes. So since we have B5, so we know B0 to B5, even though sometimes students ask me, okay, why do we have 6 boxes? Because we only have 1, 2, 3, 4. No, we have to make sure that we have all 6 because only the calculation is not used, but you will use those bits that are not here. Which one? B1 and B3. We will use it. We will shift it. So you must draw all of them, but only the ones here that is used to create B5. So B5. So first, draw all the bits. Oops. Yeah, draw all the bits, and then B5 comes from, is equivalent to B4 XOR. So you could draw the arrow, B4, put the arrow, XOR with B2. Look, XOR with B2 and also XOR with B0. So they are B0 XOR with B2 XOR B4. It becomes B5. And then the B5 is feedback, is feedback shift register, feedback into B4. But we still need to use B3 and B2 because when B5 is feedback back to B4, shift to B4, B4 is shift to B3, B3 is shift to B2, B2 and B1. Okay, let me show you the table, much easier to understand. And remember this, we are creating the key. I haven't shown you how to encrypt yet. This is the linear feedback shift register, LFSR, is used to create the key used in synchronous stream cipher. Right? So here, another example. So B4, B1, B0. How many? We need 5 Bs, 0 to 4, but only 4 box, B0, B1, B2, B3. B4 is not in the box, yeah? And the arrow means B0 XOR B1. So B0 XOR B1, this is XOR, and then it becomes B4. And the rest is shift to B3, B3 shift to B2, B2 shift to B1, B1 shift to B0, and then it becomes the key. Remember, we are creating stream of key, right, to be encrypted with the plain text to produce the ciphertext. Okay? All right, I hope you're okay. If you're not, write down your question. Okay, what should I ask during discussion? Okay, so in a table is much easier. So we have our initial state. We are trying to create the key. So this is what we are creating. This is what we are creating, the key. Okay, so this is the key that we will use for encryption. So before that, let's create the table. So B0, B1, B2, B3, B4. We're doing this. Yeah, B0, B1, B2, B3, B4. So B4 is part of the table. Just it doesn't have a box in the drawing. Okay, so initially, you must give us the first initial. So if we have 1, 2, 3, 4, 5, 5 bits, give us 5 bits lah. Yeah, the initial. Initial, that is not the key. The key is not 5 bits. The key, because it's stream. As long as you still have a plain text, if your plain text is 100 bit, you must produce 100 bits of keys. So streaming. But how to create 100 bits of key? You need to start from somewhere. So that is the initial value. So you start with only 5 bits because you only have 5 cells. Yeah, cell values. So first put the initial there. So the initial value is 10001. All right, no key yet. Okay. Okay, sorry. You don't know B4 yet. You don't know B4. Okay, you don't know B4. Okay, I think maybe, hold on. Okay. So let me let's retrace back ours. Let's start from restart. So you only need to start with the initial value of the bits that has boxes. All right? Because B4 comes from the manipulation of the value in the box. So the initial value are those in the box, not B4. All right? So we have 4 boxes, B0, B1, B2, B3. So we need to have the initial value, which is 0001. So initially, so what is B4? B4 is B1 XOR B0. So let's write it down. B1 XOR B0 here. Yeah, it is B1 XOR B0. So first, initially get the before value. So 0 XOR 1 is 1. Different value, it's true. 0 XOR 1 is 1. Okay. Then, once you fill up, you have the initial all B1 until B0 until B4, shift. Shift. B4 becomes B3, B3 becomes B2, B2 becomes B1, B1 becomes B0, B0 becomes the key, the first bit of the key. And then so now you have you don't have B4? Calculate B4. B4 is B1 XOR B0. So 0 XOR 0 is 0. And then shift again. Shift again. Shift. So this becomes here. Okay, and then calculate 0, 0 is 0, like that. That's all you do. You do until finally you will get a stream of key. So this stream of key, you will use, yeah, all this to get the plain text. So you will use it. So this output, that one, this, that's the stream. And then you will encrypt with plain text. So in this case, the encryption is just an XOR, so XOR. 1 bit key XOR with 1 bit plain text to get the ciphertext. So LFSR is a technique to create a key, a stream of key for stream cipher. Okay. So here it says, note that the key stream looks like a random sequence at first. So this looks like random sequence 1000 100. This is 30, then this is 20, and then this is 11. It looks random, but actually it is what we call pseudo-random. Not totally random, but pseudo-random. Looks like random. It's not actually random because it actually repeats. So you will see there's a pattern up to 1, 2, 3, 4, 15 bits. And then it repeats itself. So that it looks like random, but it's not totally random. So we call it pseudo-random. Pseudo-random sequence. So LFSR is actually a pseudo-random sequence, but it produced the key. So your key in the streaming, so like I said just now, if you have 100 bits of plain text, you need 100 bits of key? No. Yeah, it depends on how many cells you have. You eventually doesn't have 100, you have like maybe a pseudo-random, not maybe, you have a pseudo-random key that repeats itself, yeah, after a while. So the sequence is periodic. That is synchronous, yeah. So synchronous stream cipher, the key is independent of plain text and ciphertext. But in non-synchronous is not at the same time you key plain text, not at the same time, yeah. So non-synchronous stream cipher, the difference is that each key in the key stream, the one that you created just now in LFSR, but you need input from the previous plain text or ciphertext. But for synchronous, independent. For non-synchronous, it is dependent on the plain text. Yeah, we use the previous plain text, ciphertext, and then we do some manipulation to produce the key. I think this is the last slide. Sadaqallahul Azim. All right. So, what is the conclusion that we learned in this chapter? What do we do? Okay. So, from the beginning. So, we are learning. Actually, there's computer security at the top, right? There's computer security. So, the goal of computer security, there are 3. C, I, A. Cryptography only give services. You can achieve C and I with crypto. So, this is crypto. So, under cryptography, all right, crypto. Okay. The confidentiality we can achieve through encryption, cipher. Yeah. So, we can get this from encryption and decryption. For integrity, so far, what you have learned from the first module, integrity, we can get it from hash, yeah, hash. Okay, encryption, all right, there are 2 kinds, traditional and modern, okay, and then traditional, and this traditional is even symmetric, isn't it? Okay, so traditional symmetric key, yeah, traditional sim. In the modern, there are 2. One is symmetric. The other one later on you will learn asymmetric. And in the symmetric, we learn that there is block cipher. just now, the 6 component that made up a block cipher. And then we also learn, just briefly, we learn about stream cipher. And stream cipher, there are 2 kinds. Synchronous, where you learn LSFR, LFSR, linear feedback shift register. Yeah, independent of plaintext or ciphertext, or async, where the key created is dependent, comes from a previous plaintext or ciphertext. So now you have learned about what made up the block cipher. After these slides, the next chapter, I'll teach you a specific example of block symmetric cipher called Advanced Encryption Standard. So I hope you get the picture from the beginning until so far, chapter 5. Okay, so that's it for chapter 5. Assalamualaikum. Bye.